Hello and welcome to our Hello and welcome to our rigid body analysis video. I'm learning how to do rigid bodies in equilibrium based on the McGraw Hill 12th edition statics textbook. So the first thing is that static equilibrium means that a body under study does not translate or rotate under the loads that it's faced with. The thing that's new here is the rotation. So when we're looking at particle physics, we're focused on the translation because no matter what with the particle, your force is going through your center, right? We're only looking at a particle, and so there is no rotational element in our class. When we look at rigid bodies and we start to have more shape to it, there's more of a rotational element, and that changes how we approach equilibrium. What it'll do is it'll give us more equations. We'll have our summation of force equations that we know must be equal to 0 to prevent that translational moment. But we know that also the summation of moments at any point needs to be equal to 0 so that we don't have that rotational moment. The first thing we're going to have to do is identify the forces acting on our free body diagram. The first subset of that is identifying the boundaries of your analysis. Whatever body you want to analyze, you want to detach it from grounds or any other bodies that are impacting it. We've done this before with threads or cables by like cutting them, and where we cut them, we add a force. So we're seeing that from this 2,400 kilograms up here, we're seeing that down here. Our numbers are slightly off, but same idea. The weight due to gravity is not going to be from a ground, but that's usually going to be specified in the problem statement. Where we see grounds here that we're not used to seeing them or that we're not used to analyzing are A and B. So A is a pin joint and B is a rocker. Our first thing we'll look at is our rollers, wheels, rockers, or frictionless surfaces. With reaction supports, we want to introduce forces where the support constrains motion, meaning where the support prevents motion from happening. So in these cases, we have a pin up here, so we have some rotational freedom, and we have wheels or some ability to slide. So we have freedom in our X direction looking from this perspective. Meaning the only constraint that it's giving us is perpendicular to contact point. In this case, it would be in our Y direction. In the case of our rocker FB, it would be in the X direction because that rocker is hitting a wall, perpendicular to that wall, go out that way. Cables and links we're used to, that's a force in the known line of action. The known line of action would be the unit vector. Collars and pins, sliding pins, we're less concerned about in this class, but they do apply a force with a known line of action perpendicular to that contact point. Frictionless pins or hinges or rough surfaces are pretty common. They are going to allow rotation. There's a pin there, or you can rotate the part. What it doesn't allow, this would be bolted or welded. There's no sliding motion, there's no left and right, and there's no up and down. So we're going to add constraints along our X and our Y axes. Our fixed support, we're talking from not a material standpoint. From a material standpoint, you could push and get some deflection rotation, but you're not going to have freedom of movement. You would still have resistance, so it would still apply a force to you, right? Our fixed support, picture like a beam in a concrete base that is somewhat submerged for a little bit, and that adds that fixed support at the bottom. That applies, it doesn't allow any motion. It doesn't allow you to slide it, and it doesn't allow you to rotate it freely. And so we're going to add a force in our positive X direction, our positive Y direction, and we're going to add a moment anywhere we break a fixed support as well. So again, looking back at this example, let's specify our boundaries. Let's figure out where we want to, what we want to be the boundary of our analysis. And anywhere we make a cut, we introduce a force. So we have our force from this wire, we have a force, two forces from our pin, and one force from the rocker. The only force here that we're not seeing from making a break is from the weight of the thing, or weight of gravity in that point G. It's the only force that we're not getting from breaking a ground or a cable. A hint for approaching, right? Once we have this, we can go in with our analysis, our equilibrium analysis. One hint for approaching that is when we analyze our moments, if we pick a spot to analyze the moments that has multiple forces going through it, any force that's line of action goes through the spot that we're analyzing will have a moment impact of 0 due to 0 perpendicular distance. That will get rid of that unknown value out of your equation for your moment, and you'll have an easier time solving for some of the other unknowns because you're getting rid of unknown values from your equation. Similar to our 2 dimensions, let's go back 1 second. So if I were to analyze the moments on this figure, if I analyze the moment about point A, AX and AY would both have 0 moment impact due to 0 perpendicular distance, and then the only unknown value left would be the B value. If we were to analyze point B for our moments, B would have a moment impact of 0. AY would also have a moment impact of 0 because both of them have a perpendicular distance of 0. That would leave only AX as our unknown value in that equation. So you see how that simplifies a little bit. When we move to 3 dimensions, we add summation of forces in Z and summation of moments about the Z-axis. This gives us 6 equations that allows us to find essentially 6 unknowns in our system. Ultimately, though, summation of forces in X is summation of forces in any direction is equal to 0, and summation of moments at any point is equal to 0. Our 3D reaction supports are going to be similar to our 2D. So a ball or a frictionless surface will only apply a force perpendicular to the force where contact is made. You can't go through the floor, right? So it's adding that force to resist that falling through the floor motion. A roller on a rough surface or a wheel on a rail. So this would be like a ball that is able to rotate in any direction. These are wheels that are constrained to only rotate on one axis, and so it will constrain motion on the other 2 axes. We do still have rotation here, so we can still get that rotational element. When we look down to our rough surface and our ball socket, that is constraining motion any translational way, any sliding way. It's not constraining our rotational moment. So we have a force in the X, Y, and Z axes, but we don't have any moments applied. Here we start getting a little more complicated with applying moments and all of that. We are not going to see most of these in this class. The one that we will see is the fixed support. Similar to a 2D fixed support, it's going to apply a translational force in any direction because it does not allow any sliding or any translational movement. It's also going to apply a moment in any direction because it doesn't allow for any rotation. Okay, any questions? All right, if there are any questions, please let me know, and I'll talk to you all soon. Thank you.